In this paper, we introduce a novel method for pre-training vision VITs, known as masked autoencoders, MAE. The first step in our process involves the use of MAE to reconstruct a masked portion of the input image. We feed the visible patches of the image into the VIT encoder, which then outputs a set of feature latents. These latents, along with positional embeddings and a mask token, are passed into the MAE decoder. The decoder blocks, which share the same architecture as the encoder blocks, utilize self-attention layers. The outputs from the decoder are then passed through a fully connected layer per patch for image reconstruction. The second step in our process involves the use of cross-attention for reconstruction. We replace the self-attention mechanism in the decoder blocks with cross-attention. The queries are the output from previous decoder blocks, and the keys and values are derived from the encoded features. Our decoder employs multi-head cross-attention, where the output from the final encoder block is used as the key and value tokens for all layers of the decoder. The residual connections in each decoder block enable iterative refinement of decoded tokens. In the third step, we introduce the concept of partial reconstruction. Our method, CrossMAE, allows for efficient partial reconstruction by decoding only a random subset of the masked tokens. The reconstruction is computed on a random subset of the locations, and the loss is applied only to the decoded locations. This approach significantly reduces the computation complexity of the system. In the fourth step, we introduce inter-block attention. In MAE, we combine the feature of the last encoder block with the mask tokens as the input to the self-attention decoder. However, in CrossMAE, we introduce interblock attention, which takes a weighted sum of the visible token embeddings across different input blocks at the same spatial location. This fuses the input features from multiple blocks into one feature map for each decoder block. This allows the decoder to leverage information from multiple encoder blocks and improves the performance of CrossMAE. In conclusion, our paper primarily focuses on introducing the CrossMAE method and discussing its design choices and potential benefits. We believe that this method offers a promising approach to pre-training vision transformers and improving their performance.